Welcome to my channel. I know I mentioned on the last video about this balancing stand that I wouldn't be making any more, but my bearings finally came in and there was reasonable interest in this, so I thought I'd go ahead and do one more follow-up. This one will be short. What I've got here is a piece of a continuous cast bronze, and I'm making the sleeves for the balancing wheels. And I've got this all turned to size. I had a little bit of an interesting thing happen on this. I'm trying to shoot for about a 2/10,000ths, or what I call 2/10ths interference fit on this. So an interference fit is where the inside diameter of the one part is slightly smaller by an amount, predetermined amount, than the outside diameter of the other part. So in theory, the concentricity of the two parts after they've been pressed together is, about as good as it can get. So on this one, what happened was, this is a piece of solid bar stock. It's been bored and turned to size, and of course the conventional practice is, before making the final cut to final size, to let the part cool back down so that you get accurate dimensions. And I'm shooting for about the lightest press fit I can get. I'm shooting for about 2/10ths interference fit. So just to give you an idea of the difference between the precision bearing and the old cheap bearings. And I can hear my old shop teacher screaming at me from the other side of the room, "Quit spinning those bearings like that." God bless him. He was right, but I'm just doing this for demonstration. So there's the difference. Just a completely different animal. And I knew that, but I was testing it, and the tests showed me that it was worth continuing and buying the higher precision bearings. All right, so I'm getting this apart. I've already got the one pressed on there, and I'm going to show quickly how I went about doing this. I'm still working with my 3D printed frame. I haven't redesigned it yet or decided how to do that, but with the new bearings, I wanted to test this and get some idea of the sensitivity compared to my knife balancing stand. And I'll compare these two when I get this all put together. Okay, so just disassembling the test bearings. These are the final wheels, and I'll show you the huge difference between these tester bearings, the inexpensive tester bearings, and the new precision ones. Okay, so that's what I had there. I just used, this was just a PVC sleeve that I used before. And again, owing to some of the inaccuracy and so forth, but really most of it came from the bearings. So I've preheated my copper anvil here. And I've got my new bearings out. I haven't chilled these or anything like that, so I'm just going to slightly warm up the wheel and the sleeve and see if I can just drop them together. And it worked out well on the first one I did. And just make sure everything's clean. I've also got that little aluminum punch warmed up in case I have to tap them a little bit to get them together. If I don't get these, basically perfectly parallel, in other words, lined up exactly, if they're a little bit skewed one part to the next, they will stick and need to be driven home. So I'm hoping that doesn't happen. But a lot of times it does. So the press is nearby, but this is such a light press that I should be able to just tap it together if it comes to that. Now, it's always a good thing when doing this to not be in a hurry, and even after you've warmed the part up, to just give it a second. And see, there it is. I just didn't get it perfect, but a little tiny tap will just bring that together. What I was saying is to just let it soak for 30 seconds or something. You think the heat's going to dissipate, but what it's actually going to do is penetrate the whole part evenly. So it doesn't take very much, but it will expand out enough to allow that the bearing to drop in and be about as concentric as I'm capable of getting it anyway. Yeah, let's see how we do. Clean it off. There we go. Just right. That's the way the sleeve should have gone in. And that should be about all it takes, and that has frozen into place now. That won't come back out. Yeah, let's see how this one rotates. Now it's so completely different than the cheaper bearings. Okay, so I'll do the other one off camera and then get this assembled and give it a try and see the difference. Okay, so set up here with the intentionally wildly off balance test piece. And if you look at the other video, you can see how it was obviously determined where the heavy spot was, but it wasn't as obvious as it is now. There was a comment on the last video talking about how the poster thought it was better to use the knife balancer in this situation because the points of contact could be made more close to the flywheel, and that this design introduces the bend moment of the shaft, the actual capstan shaft, into the equation. That's correct, of course. However, I would argue that this more closely simulates the running condition of the assembly in the transport, because the spacing between the two sets of wheels can be placed in exactly the point of contact of the two bearings in the transport. So what we're actually doing here is we're including the eccentricity, we're including the bend moment of the shaft, the flexibility of the shaft, because it is flexible. All these things are flexible. And I think this is actually more representative of the rotating assembly in the transport. So what I'd like to do now is try to put some numbers to it and see just how sensitive this assembly is. Again, knowing that I don't have a machined frame. I'm still on the 3D printed frame, which is going to introduce a bunch more accuracies. But I've done a couple of things here to try and eliminate as much of that as possible. I've got the two pieces running more parallel and more square to each other. You can kind of see my arrangement there with a square and a parallel. Now, of course, this is the capstan flywheel assembly that I previously balanced on the knife stand, and I've got some random different weights of just sticky tack that I want to determine the lowest possible amount that can be measured by this. In other words, that can rotate the shaft off its balance. And now this isn't perfectly balanced either. This has its own tolerance, so it has an amount of unbalance also, but it's not very much. And sticky tack was just handy, easy to work with, easy to measure. Now in practice, I think probably what will happen is I'll rotate this thing at a speed, like this, and let it kind of find its happy spot, and then proceed to do the measurements and the balancing. But it seems like it will absolutely repeat. I've also determined that I need to kind of wiggle it into place with this assembly. Once I get everything, once all the tolerances are tightened up and I've got a solid frame and everything, this will change. I don't need this to bottom out. All I need it to do is have enough mass to rotate it off of its balance spot. It needs to overcome the inertia of it resting. And this is about half. I broke that piece in half. This is about half of what the other one was. And what I'm starting to notice now is I'm starting to notice the imbalance in, the slight amount of imbalance that exists now, because I can see it from one side to the next, and I can kind of work it one direction and the other, and more or less balance out the imbalance on this. So this is still way more weight than is necessary. You can see it just very easily senses that. And everything I'm observing here, I expect to be much better, maybe even half this amount when the final machined assembly gets done. So what I'm noticing here is that I've kind of, now I'm starting to find the actual small amount of imbalance on this assembly, and so I'm just kind of moving the position of this to see if I can if I can kind of take that out of the equation as well, but it'll take quite a bit of time to do that. And it's not worth it at this point with the 3D printed frame. But the point is, the weight here is more than sufficient to move this off its okay. Just like I say, you just have to keep moving things around and maybe pretty close. Let's see. Okay, so there, very obvious. We're not actually counteracting the imbalance. We're kind of exaggerating it. So let's just put that right on one of my balancing marks. See what happens there. Kind of tap everything, get it settled. This stand can also be used to indicate the run out of the flywheel, because they do go out of round occasionally, especially the cast ones. And so instead of having to take the time to set it up in a lathe, this could do the same thing in a much shorter amount of time. So there's a dual purpose to this. And of course, I'm finding that I really have to settle everything in for this to work. And again, that will all disappear with the machined frame. Okay, so let's say that this amount of weight is our reference for now. Let's just measure it and see how much it weighs. And then we'll compare it to the balance, the knife balancer, and see how sensitive that is. Yeah, let's just try to get you in frame. Okay, so I think I can say that this is absolutely sensitive to 0.0605 grains. Let's call it 0.6. I expect it to be, and there was the first one that I put on. So, about double. But 0.06 grains can absolutely move this shaft off to its balance spot. Okay, we'll call it 0.06. Okay, let's try it on the knife stand and see what that can do. Okay, you can see it's pretty well balanced. I can pretty much put it in any position and it will remain there. Obviously, the disadvantage of this is the very tiny amount of space between the shaft and the knife edge, necessarily so. And the constant having to reposition it. Okay, so there's the 0.06 gram sticky tack from the previous use. Have to keep it from interfering on the knife edge. What I'll just put a mark opposite where I've placed the weight so that you can kind of see it on camera. Space it off. Obviously, no problem with that. I expect this to be more sensitive. I just don't know by how much. Okay, so very obvious. Of course, at this point, the motion also is smoother than the other, but there's a lot more running parts in the other. There's actually only one running part on this. Okay, so that's clearly detectable on this one. Let's just cut this piece in half and see if it can detect half that amount of weight. So roughly 0.03 grams. Let's see if that'll stay there. Okay, there's my spacing. Looks like it's iffy. Again, I might be compounding or, reducing the already small amount of imbalance. The spacing's always a problem on this, and that's one of the issues that I've run into, causing me to want to, improve it. So I think I can say with some confidence that I've reached the practical limit of what this knife balancing stand is able to achieve. And we'll measure that, but I'm assuming it's going to be somewhere around that 0.03 gram range. Which isn't very much. Come on. There it goes. So it looks like this is the practical limit of the range on this scale also. Let's do it like this. Yeah, so about 0.03 grams. Just somewhere in between 0.03 and 0.06. It looks like both of these stands are able to resolve. So that's it for this one. Thank you for watching again, and I look forward to your comments. See you again here soon.